So what is meteorology then? It sounds like it should be the study of meteors, but we know it's not. It's what we call the study of weather and climate, even though there is a branch of science called climatology. But that's neither here nor there. It comes from the Greek word meteoros, and to the Greeks, a meteor was anything that was high in the air. So it could be anything falling from the air, or it could be any process that was taking place in the air, like the formation of a rainbow or formation of clouds. Aristotle then wrote a book called Meteorology in 350 BCE. And this was like a compendium of all things that were known at the time for processes that took place in the atmosphere, for any phenomena that were being seen in the atmosphere. And he called that book Meteorology, and that's why we get that term for the study of weather. One of the pet peeves of people that are into weather is that some people don't distinguish between the two, between weather and climate. They think that those are the same things. You hear a lot of our politicians talking about this. I remember one time there was this big snowstorm in Washington, D.C., and James Inhofe, who is a big climate change denier, brought a snowball into the Senate room and threw it out and said, "Oh, here's your global warming," intimating that because it was snowing, that there wasn't any global warming. Well, that just shows that he has a misunderstanding of weather and climate. Weather, the day-to-day condition of the atmosphere, sometimes the minute-by-minute condition of the atmosphere. We know that there are days here in the Central Valley where we have very unstable days, and it might be sunny one minute and then pouring rain or maybe hail the next minute. So those things that we measure in order to forecast weather or determine weather are temperature, pressure, precipitation, humidity, cloud cover, wind speed, and direction. Those are the biggies. But again, there are other things that we look at too, like greatest 24-hour rainfall or snowfall event, number of days with dense fog. One of the things that we're obsessed with here in Sacramento is how many days in a row did the temperature reach over 100 degrees, or how many days have we gone without rain? Then climate are those atmospheric conditions over here averaged over a long period of time. And by international convention, that long period of time has been agreed to be 30 years. So you might think, okay, why 30 years? Why do you need that long to determine what the climate of an area is? And just think about this. What if you based the climate of an area on a year when there was this extreme weather, like maybe an abnormally large amount of rain that fell, or maybe an abnormally cooler period of time? So the 30 years are to cancel out, to moderate those extremes. Then the difference between weather and climate, then it's just a matter of time. Weather short term, climate the average of weather. And somebody said that Mark Twain said this. I don't know that he really did. Mark Twain has been attributed to a lot of sayings, but climate is what you expect, weather is what you get. So we might go to Miami and we think, oh, it's going to be warm, it's going to be sunny, we're going to be on the beach, we're going to get a suntan. But we go there and there's a hurricane. Okay, what we had in mind was the climate, but what we actually got was the weather. The hurricane is the weather. And this is weather. This is a mid-latitude cyclone, and it brings different weather to different places as it travels across the country. or it could be moving up this way. But depending on where you are in relation to the cold front and the warm sector, the cold sector, you're going to have variable weather. The US has some of the most variable weather in the world, mainly because we're, a large country. So there's a huge swath that can be having different, because it's such a huge swath, there are areas that can be having totally different weather. This is a typical weather map showing cold fronts, warm fronts, some stationary fronts in here. The H's, the big H's are the high pressure systems. The red L's are low pressure systems. So we'll learn about this later when we talk about mid-latitude cyclones and frontal systems. But just so you know right now, the blue line with the triangles on it, that denotes a cold front. So the triangles are pointing in the direction that the cold air is moving. So cold air would be back here, and it's moving from the north to the south. And it's moving into an area of warmer air. Now, it might not be warm, it might not be in the 80s or 90s, but it's going to be warmer than the air behind it. The red line here, that is a warm front. Warm air back here, and that warm air is moving this direction into an area of cooler air. Cold air here, another cold front moving down, and then we have this cold front that has moved offshore in this direction. And this shows the same thing, but we're seeing temperatures. If you go back and look at the cold and warm fronts, you see where the warmer temperatures are back here compared to where we have the colder temperatures over here. And then this is a climate map of the US. So the weather maps we expect to change. Even with the little blip in time that the weather map is representing, the next minute or the next hour, things are going to change. The atmosphere is dynamic, so these things aren't standing still except for a stationary front. Things are moving. A climate map we do not expect to change as much, but with global warming, we are seeing that climatic zones are changing. So one of these days, hopefully in the near future, atlases will show how these zones have changed. So what's the importance of the atmosphere? Well, first of all, there would be no life on Earth without an atmosphere. We would have no colorful skies. In fact, there would be no sky. You've got to have an atmosphere to have a sky. No sound. Sound has to have something to move through. That's why I always get a kick out of these space movies where they have these spaceships fighting it out and you get all of these sounds from explosions. But it would be a pretty boring movie if, you're just sitting there watching lights flash back and forth without any sound to it. No weather. Got to have an atmosphere to have weather. No water. And there would be temperature extremes from day to night. So it would be a totally different type of world. We wouldn't be here to know anything about it, though, without an atmosphere. This is the moon. These are astronauts that are on the moon, and you see that the astronaut is standing in sunlight. That glow is from sunlight coming through. But look at the sky. Oh, no sky. Look at space. Uh, totally black because there's no atmosphere to scatter that sunlight. So that's what it would look like on Earth if we didn't have a sky. So this is a view of the space shuttle when we had space shuttles going back and forth up to the space station or just orbiting the Earth. This is the return of one, and you see that it's coming into the atmosphere, and they meteors when they come into the atmosphere, catching on fire. So did the space shuttle. It's just that there were protective tiles to keep it from burning up, but there was one called Columbia that one of the tiles had been impacted on launch, and when they re-entered orbit, the fire brought on by friction with the space shuttle and air particles got in between the shuttle and the tile that was supposed to protect it, and it burned up and broke up over Texas, killing all on board. But you can see the atmosphere. You can see how it's thicker here toward the bottom, and these gradations in color as we get fewer and fewer molecules as we get higher and higher in the atmosphere. And then we see clouds here. And then here's another view. You can see that our atmosphere is can be a very turbulent place. Sometimes it's referred to as an ocean of air. And I like that description because when we're talking about the ocean, we have no problem understanding that there's turbulence in the oceans. There are waves in the ocean. There are eddies in the ocean. There are currents in the ocean. The atmosphere is the same way. Water is a fluid, and air is also a fluid. So fluid mechanics would apply to what's happening here. And what we're seeing is a huge amount of turbulence here. This is a hurricane. Notice that nice counterclockwise circulation there. And then out from that hurricane, we see these rain bands. Anytime you see a cloud that is growing up like this, growing up horizontally in the atmosphere, that indicates instability. And if we want weather, wicked weather or unstable weather, we have to have rising air. So these are cumulus clouds. Each of these are thunderstorms here. So there's a line of thunderstorms. Those are the rain bands out in front of the hurricane itself. And then we see just some horizontal type clouds here, and those represent more stability in the atmosphere. This is another view of the atmosphere. I think this is SpaceX rocket coming back to Earth, and we see again the gradations in color of the atmosphere. This is where we are down here. This is the troposphere. 99.9% of all clouds are going to occur in the troposphere. What are the major components in our atmosphere? You might be surprised to know that oxygen is not the most abundant gas in our atmosphere. It's nitrogen at 78%. Oxygen is down there at 21%. So our air, Earth's air, is composed of these things. These are considered to be the ones that are non-variable. These amounts stay very similar. Nitrogen 78, oxygen 21. And it's important that these two stay in balance with each other, because if oxygen was up around 23%, everything would be burning. Even the wettest rainforests could burn. Oxygen is an oxidizer. That means that it supports combustion. If it were down around 19%, we wouldn't have anything burning. You wouldn't be able to have a campfire. You wouldn't be able to, light a match because there wouldn't be enough oxygen in the atmosphere. So those two have been constant for about the past 400, 500 million years or so. Then the next one is argon. And look at how that amount goes down, 0.93%. Argon is an inert gas, meaning that it doesn't like to react with anything else. And you might be wondering, well, okay, how did it get into the atmosphere? Well, as a geologist, I'm going to have to tell you how. There are some rocks that contain radioactive potassium. I'll just initial potassium K, potassium 40. If something is radioactive, that means that there are nuclear reactions that are taking place. And when there are reactions that are taking place in the nucleus, the element can change as the nucleus begins to break down, or as these particles are removed from the nucleus or added to the nucleus. So radioactive potassium would be the parent, and we say that it is unstable. And over time, it will disintegrate into argon. So argon would be the daughter, DAUGHTER, and it is stable. So as radioactive potassium in rocks has decayed, argon has accumulated in the atmosphere, and that's how it got there. Then there are those gases that vary in their amount in the atmosphere, and one of them is carbon dioxide, CO2, carbon and two atoms of oxygen. Carbon dioxide is the one that is implicated mainly. There are some others that we'll talk about later, but CO2 is the major culprit in global heating. So this amount just keeps rising. I've put some numbers in here from years back. So in 2005, it was 0.037%. In 2010, it was 0.039 or 390 parts per million. In 2014, it was 395 parts per million. In 2015, it was 400 parts per million. In 2016, 401 parts per million. September of 17, 402. October of 18, 405. And let's bounce over here to January 2021. 415 parts per million compared to January 25th, 2021, which was 412.4 parts per million. So you can see that it just keeps rising. So what's the big deal with that? Well, you have to keep in mind that 350 parts per million is what we need to be at. That's what it was when civilization started. If we want a world like the one in which civilization developed, then we need to be back there at 350. But we have blown by that number without a second look. If it were up to me, every night, every newscast, every night, it would lead off with the CO2 numbers. It's all this is just being ignored. We just blithely go about our everyday life and never think about this stuff. But it's having a huge impact. And we'll talk about why. How does CO2 get into the atmosphere? Is it natural? Yes. Are there man-made causes? Yes. And it's the man-made contribution that's the big problem. We'll talk more about CO2, way more. You'll probably get sick of hearing about it. So what about the other things that are in the atmosphere? Oh my gosh, water vapor. Water vapor will vary from 0 to 4%. And just like CO2, water vapor is a greenhouse gas. Greenhouse gas, I'll abbreviate it that way so we don't have to always say greenhouse gases. Greenhouse gases absorb heat, absorb long wave radiation. Or what we would call heat. So the more of these that we have in our atmosphere, the more heat that's going to be absorbed from the Earth's surface. Water vapor is the most important gas for weather processes. Water vapor is the fuel for weather. Without water vapor, we're not going to have any weather as we know it. It's not like on Venus where it rains sulfuric acid, thankfully. Here on Earth, it rains water out of the sky. And it is an energy transport mechanism. Water vapor has energy locked up in the molecule. More about that later too. Then what else is in the atmosphere? Aerosols. Aerosols are tiny teeny tiny solid and liquid particles. It could be dust, it could be ash, it could be pollen, it can be salt. And a lot of times we think of this as pollution, and it is pollution when we get too much of this stuff, but we have to have some of these things in order for clouds to form because they act as condensation nuclei. That water vapor in the atmosphere needs something to condense upon. So it will condense on dust, it will condense on ash. So that brings me to the recipe for a cloud. Recipe for a cloud. What do I need to make a cloud? First of all, I need water vapor, and then I need condensation nuclei, and the third thing that I need, cooling temperatures. All those we need in the right combo to make a cloud. Then ozone, O plus O plus O, 3 oxygens that have chemically reacted to each other, that have formed bonds, 3 oxygens that have formed bonds. We have this love-hate relationship going on with ozone because at ground level we hate it. It's a pollutant. This is the thing that's implicated in those spare the air days that we have. If you have an allergy, if you have emphysema, maybe you have an immune system that is impacted somehow, ozone can be very bad for you. It stings your eyes, you breathe it in, and it's very reactive, and it likes to react with moisture. So you have moisture in your nose, you have moisture in your throat, you have moisture in your eyes, and that's why we have stingy eyes. We start coughing or sneezing when we come in contact with ozone. Plants don't like ozone either. Rubber products don't like ozone. But in the stratosphere, oh man, we are so grateful that ozone is up there because it protects us from harmful ultraviolet C radiation. It wasn't that oxygen accumulated in our atmosphere, and that's what allowed things to come out of the ocean and more diverse life to evolve. It was the formation of ozone in our atmosphere. Things couldn't crawl out of the ocean because they would have been fried by the UVC radiation. But when ozone accumulated in our atmosphere, it protected things from that radiation. So we hate it at the surface, but we love it when it's in the stratosphere.